We are talking about Turing computable functions. When I got up this morning, I got a news article in my algorithmic Google News feed that told me that there is a new opera about Alan Turing. They must know that I'm into Turing. Check it out if you're into the opera world. I'm not especially into the opera world, but apparently there's a Turing opera coming out. He has become a fairly popular figure lately, more so than other mathematicians of the day. Anyway, we're talking about Turing computable functions. That is a function of strings, typically, which you can compute on a Turing machine. I wanted to do another example. Maybe I'll just refresh our memory from last time. We had a function which worked like this: f of b to the n a b to the n equals b to the n a squared b to the n. This is what we did at the end last time. Remember, what this means is this is a function which is supposed to work like if you start, it's a Turing machine where if you start with b to the n followed by a followed by b to the n on the tape, then the Turing machine will do its thing and eventually stop with this on the tape, the answer on the tape. So you start with the some kind of input, and this machine does not have an accepting state. It doesn't accept or reject. It just does some stuff and then leaves the answer on the tape. And the strategy that we used for this one was you have to somehow insert an extra a in the middle, which there's not really an insertion operation that a Turing machine is allowed to do. You have to just, in this case, move yourself over here, change the first of these b's to another a, and then keep on going to the end and insert an extra b on the end. That's how you would convert this string into something that looks like that. I'm going to do one that's a little fancier than that. This you could think of as a slight variation of that one. So that was last time. The whole concept, though, is make a Turing machine which computes the answers of certain functions. Here's another one, f of, how about this? F of x cx equals xx, where x is in AB star. So this is a function which starts with a string of a's and b's with like a c stuck in the middle, and it just removes the c which is in the middle. That sounds simpler when I say it that way. Just remove the c in the middle. You cannot just change the c in the middle to a blank, because then you end up with a blank in the middle of the tape, which is not what you want. You want to end up with xx. So for example, as an example, if I had f of a, b, a, c, a, b, a, the answer should be a, b, a, b, a, right? You cannot get there just by blanking the c in the middle. You have to actually, you have to sort of blank the c if you like, but then you got to move these guys over by one, right? All of those letters have to be pushed to the left by one position. Can we do it? I guess. Oh, I can do it. Yeah, let's see if we can make that work out. So, start in my starting state. Actually, when you start, it's not so hard to say what should you do when you start. I would say move yourself past all of this stuff until you get to the C. This stuff over here doesn't really matter, and we want it to stay like it is on the tape. So I'm going to move to the right through A's and B's. Those are the initial A's and B's, like the first X, which we don't want to modify. Once you get to a C is when it gets real, right? That's when you actually start doing stuff. So the C here, anyone want to suggest a strategy? Yeah?
I don't know if this works now, but I was initially thinking, could you somehow, I don't know, remember sort of, kind of keep track of the first string and then just rewrite it starting on top of the C. Oh. I don't know if that's possible. That's not possible at this point, but at this point.
Yeah, that is considerably harder than what I had in mind. Although, I mean, it is true, you could do this by marking. You could say, see this A, mark it off, move over, and put an A here. Move back to the leftmost unmarked letter, and then continue doing that. That could be made to work, although there's anyone have an easier strategy than that? I will use the fact that you have that string right here already, rather than this copy of it over here, which is not terribly useful. It's easier to use this copy of that string. Any idea? Yeah?
Would you like go past the C, read the A, and then go back and change it to A, and then like go past the A, read the B, like that?
Yeah, I would say just like skip over this C. You can do whatever you want to it the first time through. But then each of these letters, you copy them one place to the left. So I copy this A once to the left, then I copy this B once to the left, and so on. So when I first see this C, I mean, I guess I don't know. You can do whatever you want to this C. You could blank it the first time through, or you could leave it like a C. Maybe I'll blank it. All right. Get rid of that C. Moving to the right, next I will be pointed at this A. Really what we want to do at this point is move to the left by one position and stick an A there if this letter was an A, or stick a B there if this letter was a B. So I'm going to make a little 2 branches because I'm going to behave differently. If the letter I'm looking at right now is an A, I copy an A to the left. If it was a B, I copy a B to the left. So here I'm going to say A, L. And then in that state, whatever happens, I replace it with an A, right? So if it was a B to the left, I make it an A. If it was a A to the left, I make it an A. And I suppose it could be a blank if it was that particular one that I blanked out. So, and really after I do that, I want to just move back to the right and continue the whole thing. I think I need an extra state for that. I think here's the structure that it's going to have. Seeing this A, you go to the left, and then whatever you see there, you replace with an A. So if it was a B, I'll make it an A. If it was an A, I keep it an A. And if it was a blank, which is possible just because of this arrow here, I might have made a blank in there. Anyway, I make it an A. And then move to the right. So after this arrow, I will be pointing at the letter which I just copied to the left. And then whatever that is, I want to move to the right once more and then back to this state. So it'll say like this. AAR, or BBR. And then I'm ready to copy the next letter. So the sort of the other track of this branch would be BBL, and then this one is blank BR, A, BR, B, BR, right? That's the state in which we are copying a little b one position to the left. It's a little complicated, maybe. I don't know. All right. This little loop there will go through and copy every letter to the left. Anyone want to say where does it end? What should we do? How do you tell where it's going to stop? Eventually, you're moving yourself to the right, so eventually you'll hit a blank.
Once you hit a blank.
Yes. Where are you going to encounter a blank?
In the middle C.
This one here?
Yeah.
Yeah, I think here is where you'll see a blank at some point. When you see a blank, should you just... So if you want to just stop when you see a blank, it would be like this, something like BBR, and then... Stop. Remember, this machine is not meant to have an accepting state. It's meant to just stop. Is that actually what we want to happen?
You want to replace the last letter that you saw with a blank, so it's not like an
Yeah, actually, if you think about it, this sort of copying things to the left every time, it's going to leave an extra letter on the end. If your string was, for instance, A, C, A, it's very simple. You would, the first loop would sort of change the C to a B, then I copy this A into that position, and it'll now say A, and then, of course, the blank. The head will get there, but there's still like a leftover letter at the end, which got copied, but never blanked out. So we need to do actually that BBR. I think actually it's going to be better if I make it a BBL, because I want to go back here and just blank one last letter. So I'm going to make this a BBL. Sorry about that. And then if there's an A on the end there, I'll blank it. If there's a B on the end there, I'll blank it. And I suppose it's possible there could have just been a C there. If the entire original string was just a C, that could happen. That's sort of a special case. All right, I think that'll do it. This is a rare situation in which we have an arrow like this with a BBL, and then there's still more stuff to do afterwards. Sometimes it happens. There was an extra letter on the end which has to get blanked out. All right, a little tricky. Yes?
So since you blanked the C initially though,
Yeah.
Do you need to have that last?
Oh, yeah. Yeah, you're right. Since I blanked the C, this is never going to happen. There can't be a C on the tape right there. Yep. Whoa. All right. It's too fancy for me. Get rid of that. Yep, you're right. You don't need that. I mean, I don't think it would hurt, but you don't need it. All right. Excellent. Great. That was the last example of these kind of simple string function computations that I wanted to do. I want to talk about some more like recognizable mathematical functions, in particular some functions for arithmetic, by which I mean like adding and multiplying, although really we're just going to do adding. Arithmetic on Turing machines. All the examples of arithmetic we're going to do are going to be using binary numbers, just because it's easier. It's easier in terms of how many states you need. The alphabet is much smaller. If the alphabet has only 0 and 1 versus 0 through 9 is many. It makes all the diagrams more complicated, but you would use all the same idea. How about for binary numbers? Let's make a Turing machine for f of x equals 2x. I mean multiply by 2 for binary numbers. So for example, if I have the number like 101 in binary, which is, anybody remember how to convert binary to decimal? What number is that in base 10? 5, yeah. You think of each digit represents a power of 2. So the ones digit really is like a ones digit. The next digit over is 2s. The next digit over is 4s. So what I see here is a 4 and a 1 and no 2. So this is 5. And what's 2 times that would be 10. How do you write 10 in binary? The next digit over would be 8s. You have to think about how can I make 10 by adding together 8s, 4s, 2s, and 1s?
8 and 2.
Yeah, 10 would be an 8 and a 2. So as a binary number, it would look like this. That means an 8 and a 2 is 10 in decimal. So what I mean over here, these are decimal, base 10. These are binaries. I know it looks weird when I write 101 equals 5. All right. Any ideas about how would you think about it in terms of binary numbers? What does it look like when you multiply a number by 2 in terms of its binary representation? It's similar to in base 10 when you multiply a number by 10. Yeah, what are you going to say?
Do you add a 0 to the end?
Yeah, you just stick a 0 on the end of it. Just like in base 10, adding a 0 onto the end of a number is the same as multiplication by 10 because the effect is to increase the exponent of all the 10s. And in binary, adding a 0 on the end is the same as multiplying by 2 because the effect is to increase the exponent on all the powers of 2. These guys, they would all sort of shift over to the left. So anyway, to multiply by 2, we just add 0 on the right end of the number. And so this is actually pretty easy to do on a Turing machine, right? You just start with x, whatever your binary number is, you run all the way to the end of the string and replace a blank with a 0, and that's it. So something like, you start by going all the way to the end of the string. The string is either 0s or 1s, right? And then when you see a blank, you make it a 0. And that's it. This is Turing machine multiplies a number by 2 in binary. This loop here is keeping the entire number like it is, moving all the way to the end. Once you get to the end, whatever the last position would have been a blank, you change it to a 0, and then you stop.
But we need to know binary for the quiz or test.
Yeah. Yes. I mean, nothing too fancy. You should know that multiplication by 2 is the same as putting a 0 on the end. I don't think you would need to know necessarily how to convert a number from binary to base 10. I certainly wouldn't just ask you to do that as a whole question on its own. You should. I mean, I hope that you could do that if you had to. But that's a pretty ambiguous answer, isn't it? I don't know. Yes or no, maybe. I'm still trying to think about what an appropriate answer to that question is. I don't know. You should be able to do simple things like this. Let's leave it at that for now. That's multiplying by 2. How about, let's try a different one. How about f of x equals x plus 1? That's just adding 1 to a number written in binary. This is slightly trickier. For example, if, let's say x was this number, 0, 1, 1, 0, 1, 0. Actually, we wouldn't write the initial 0 there. But if that was x, then x plus 1 in binary, can anybody say? You should not try to convert to decimal and then add 1 and then back convert to binary. Just add 1 to the binary. This is not a trick question. Yeah.
If the last number is a 0, you just make it a 1.
Yeah, so in this particular case, if it was 11010, the answer after adding 1 would look like that. What if the last digit is a 1? If it was, say, 11011, now you got to carry, right? Is that what you were going to say? Yeah, you got to carry the 1. And actually, in this particular example, it's like a double carry, right? You carry the 1 over, and then you got to carry it again. So can anyone tell me the answer? I add 1 over here, which makes that a 0, and then I carry to the left.
Would it just be 1, 1, 0?
1, 1, 1, 0?
Add another 1. Oh, no, 0.
How about another 0? Yeah, this is how you would do it. If I were writing this out, look at that perfect circle. If I were writing that out, it would look like 11011 plus 1, like that. And I go 1 plus 1 is 0, carry the 1. Another 1 plus 1 is 0, carry the 1. 1 plus 0 is 1, and then I have these two ones, like that. It's just like when you were a kid, only 1 plus 1 is 1, 0. All right? So it is slightly complicated. You have to carry, and you may have to continue to carry as long as you continue to see more and more ones as you go. But it's not so difficult. Let's see if we can try and write this out. First of all, I will have you notice, this is something that everybody knows, really when it comes to adding 1 to a number, you need to start on the right and work your way to the left. So what I'm going to do first of all is move all the way to the right of the string, because we can't handle the left end first when we're adding. Move all the way to the right end of the string. Anybody know why that is, by the way, when we write numbers? It's kind of the... you ever feel like we write numbers backwards? I don't know. You know? Because the beginning of the number, like as the number gets bigger, it grows to the left, not to the right. This is backwards from words. As a word gets bigger, it grows on the right. Isn't that? You ever think about that? Yeah, when you write a word, like as I write, I move from left to right. Birthday, that's not a word. I meant to write this. But as I write a number,
We know you still go from.
I don't really mean as my hand moves. I would still write left to right as my hand moves. But as I think about like a small number turning into a bigger number, it grows the other way,
That's true.
right?
Even in Excel.
Even in Excel.
Yeah, like in Excel, like when the number always starts on the, like.
Because they
right-hand
write a
side.
line that
Yeah, like
by
right
default.
at the
Yeah,
bottom.
that's not really what I was thinking of.
Well,
But,
to
yeah.
be fair, you go from left or right.
Strain. There is a reason for this because
Because, for example, if you read something at 1,000, so for example, you have a number like 10,233.
yes.
When you immediately look at that, you know it's around 10,000 because you look at the first one.
Yeah. Yeah, you could say the leftmost digit is like the most significant one. It has the greatest value.
Yeah, so
Yes, that's true. I think the true reason that we do it this way is because these are Arabic numbers. And these numbers were first used in the context of a right to left writing. The way that the Arabs wrote everything and continue to write everything is right to left. And so the numbers make more sense in that system. And it may be, I assume, if the Turing machine was invented by Arabs, they would have started the head on the right end of the string rather than we always start it on the left end of the string. Think about that. Anyway, we begin by moving all the way to the right end of the number, right? Because that's where the action happens. So I'm going to go 0, 0, R, 1, 1, R. Right, and then eventually we encounter a blank, and I say BBL. So now that's just a little nuisance because of the backwards representation of numbers, or alternatively the backwards direction that the Turing machine is working. Now we are on the rightmost end of the string, and I would say if the rightmost digit of the number is a 0, then you don't really have to do much of anything. You can just say 0, 1, R, and stop, right? If the rightmost digit of the number is a 0, you make it a 1, and you stop. What if the rightmost digit is not a 0? Yeah?
Then you like.
It would
I
be
guess
like
you-
here,
I
for
guess
instance.
You make it a 0.
Make it a
Go
0.
left.
Mhm.
And if that's a 1, make that one a 0. And then go left. And then once you hit a 0, make that 0 a 1.
Yeah. So when you see a 1, you make it a 0, and then go left again. And you do that again and again until eventually you actually do hit a 0. Make that a 1, and then it stops. All of that sounds a little complicated, but check it out. That's just this. If you see a 1, you make it a 0 and move left, and you just keep on doing that until eventually you see a 0, you make it a 1, and you move right. That's all there is to it. One slight technicality is this. I'm going to also put blank 1R there. Anybody have an idea? Why is that necessary?
Because if you start with command and then it goes into way, so the first place would just be
Yeah, if you carry all the way and you have to make a new digit at the end, that new digit will go into a space which used to be blank. And so this is necessary to put right there. All right, great. So this is actually maybe simpler than it seemed like it was going to be. I don't know. This is the Turing machine which adds 1. How about, can you guys try a Turing machine which subtracts 1? So you try f of x equals x minus 1. And I'm just going to say you can assume that x is actually greater than 0. Of course, if x is 0, then it's not clear what that even means. But, because I don't want to think about negatives. You've got to borrow, right? Maybe I'll write some helpful examples here.
Professor Stefan, whenever we do math with these, is it always going to be finite?
Math? You mean like arithmetic?
Yeah.
Yeah, pretty much. I mean, it's not hard to do. It's just really annoying. If you do this in base 10,
I guess you have to do like,
you need
count for 10 digits.
Yeah,
Right.
you need like labels, 10 different labels on every arrow, which is it's not any harder. Looks like everybody's doing great. Can we talk about them? This is my setup, without much thought. You got to start with that, which will move yourself all the way to the end of the number, all the way to the rightmost end. And then you'll notice if you look at my helpful examples here, if your number actually does end with a 1, all you got to do is change it to a 0. So that will look something like 1, 0, R, and you're done. If it ends with a 0, you change it to a 1, and then you move to the left, and you continue doing that until you get to a 1, which you can change to a 0. So really, it's basically the same as what we just did. It's like that, right? Almost exactly the same as before. Just everything is slightly different. Yes?
I was wondering, I kind of wrote that, but I don't know if it's true. Is there a case like with the other one where what if you go all the way through, making it all
Yeah.
ones?
I think it's not that the only way you could go all the way, like get to a blank in this state, is if every digit of the original number was all zeros. And that's why I disallowed that.
Okay.
That means the original number was equal to 0, and you're trying to subtract 1 from 0.
There's what happens if it's like it's 1 and then over 0. Then you subtract 1, it would be over 1, but you're missing the 1. For example, 100 minus 1 would be 11. Right? You can't
Oh,
write
then
0.
yeah. So that's true. If the number was this, if it was this, then when this Turing machine runs, the answer would turn out like this.
0.
It would have a 0 on the left side.
Sure,
That's
you
true.
take care of that case.
I don't care about that case. If you want to take care of that, you could add some extra stuff over here that.
Because when you reach that, you go to the left.
Yeah, if you make it's not so hard, I guess. If this R was a L instead,
and
right?
You check all line.
Yeah, right. And then you could do B0 R. I guess that would do it. Yeah, if you wanted to.
Not B0. It's B
No?
B.
Oh, 0 BR, right? Because you.
Because when you reach the blank, you are at the blank line. You have to step back to the right.
Yes, you're right. Yes. Thank you. Yeah, so you go back 1 and then 0 blank R. Is that what you had in mind? Yes, I agree. Here you've stepped all the way off the left side, so it's still a blank. You move back once and blank out the leading 0. Yeah, generally I don't really care about extra zeros on the end. Yeah.
Do you need to have that middle blank right step?
This here? This?
Or the second one, yeah. Like, is that, because once you do, like, go through the entire 0.
So in my opinion, all of that is optional.
Like, if you were to do that, though, you still need that blank step. I'm just thinking, like, once you hit that 1 and you turn to a 0, I guess you have to put 0. Yeah, that's true.
Yeah, you do need all of this if you want to do it at
There's
all.
Also, you need also the case for when there's something else before it. Because this only account for the blank. We need another arrow. Like from the optional one, there
Yeah.
should be 2 arrows. One for when it's blank and one for when it's not like no than one top. Yeah, that. We need another arrow for when it's not blank.
When it's not blank, you don't have to do anything else,
Oh yeah.
and so the
You
machine
don't
will
have
stop.
things like-
Yeah, right. Yep. All right, excellent. So Turing machines, they can add 1 and subtract 1. These are, I suppose, interesting operations, although it would be nicer to be able to, if you wanted to do fancier types of arithmetic. What about functions of several variables, like 2 variables, say? Or functions of several parameters, if you want to use a more computer science type terminology, like for instance something like plus of 37 and 42. Obviously that's not how we usually write 37 plus 42, but I'm trying to think of it as a function which takes 2 separate inputs and does something to them, and you get the answer is 79, right?
How is it on the terminal?
So this is what I want to talk about. How could you actually model a function like this, which has 2 inputs? How could you translate that into a Turing machine computation? The question really is, how would you represent this on the tape as the input? And there are a few different strategies. So this could be, we could just write on the tape 37 comma 42, like actually put the comma there on the tape, and then the Turing machine would be able to tell what's the separation between the first input and the second input. Oftentimes this is done with some kind of special separator character, and people like to use the hashtag as a generic kind of separator. So everything before the hashtag is the first input, and everything after the hashtag is the second input. So we could write it like that on the tape. This is one way that you could specify a function with 2 inputs by just separating them with some separator symbol. Or, if convenient, we could stack them. Like, this is going to look weird, but 3, 4, and then 7, 2. Now, those look kind of like fractions. I don't mean them as fractions. I just mean they are the the digits of the inputs stacked on top of one another. Why would you want to stack the digits? Well, actually, if your goal is to add numbers together, then you do want to stack the digits, just because that's the most convenient format for adding or subtracting or multiplying or whatever else. So actually, stacked inputs is going to be a very convenient way to try to represent simple arithmetic functions using Turing machines. So if convenient, for other operations, it's not helpful to stack, but for addition and subtraction, it certainly is helpful to stack them up. So I want to try some simple functions using stacked inputs. Binary, of course. Like I said before, you could do all of these things in base 10. It's just much more of a hassle. All of our arrows here, which have to handle for certain things happen if it's a 0, certain things happen if it's a 1. We have basically 2 alternatives. If you're trying to do it in base 10, you need 10 different alternatives, and almost all of them they look the same as each other. It's just tedious to do it in base 10, much simpler to do it in binary. Anyway, let's try a Turing machine this is a low-level kind of computer operation. Bitwise and, I'll write and in all caps. The operation is bitwise and. That is, if I take 2 binary strings, say 0, 1, 1, how about 0, 0, 1, 1, 0, and 1, 0, 1, 0, 1. 2 strings of the same length, binary. Bitwise and means that you combine these 2 strings by doing and, viewing the 0 as a false and the 1 as a true. You combine them using and, sort of digit by digit or bit by bit. It means we sort of do it like, I would write this down. If I had to do this on paper, I would write like this, stack them up. And then rather than adding them as binary numbers, which you could do, I want to do the and operation vertically here. And so digit by digit, here there's not going to be any carries, so actually you can do this from left to right if you want. You go 0 and 1, which is 0. I view 0 as a false and 1 as a true. 0 and 0 is 0. Yeah. 1 and 1 is, I hope you all remember how and works. The only thing where it's going to give you a 1 is if you have 2 1s to begin with. Then 1 and 0 is 0. 0 and 1 is 0. Right? This is how the bitwise and works. This is very easy to do if your inputs are stacked, because it's exactly like what I wrote there, and you can just go left to right across the stacks and evaluate them one at a time. So let's try it out. Unlike the addition, we don't have to run all the way to the rightmost end because there are no carries that can possibly happen here. You might as well just start at the left and go to the right. In fact, it turns out I can do the entire machine basically with a single loop. And what I'm going to do is just write down what are the possible inputs here. If you see 0 stacked with 0 on the tape, what should the answer be in that position? It should be a 0. So I'm going to do that, right? That says if you see a 0 stacked with a 0 on the tape, the answer in that digit is 0, and then move to the right. If I see, and I'm just going to write down all the possibilities. 1 0 should be a 0, and 1 1 should be a 1. Right? Depending on what the input is, you just say what the answer is, bit by bit, and you move to the right. When you get to the end, what happens? You see a blank. Actually, you don't even need another state here. Once you get to a blank, the whole thing stops, and you're done, right? Pretty great. This is the bitwise AND. Very simple, using stacked inputs. Could you do the bitwise OR? Yeah, actually, almost nothing would change. It's just these answers here you would change according to OR. It would say 0, 1, 1, 1. That would be the difference if you wanted to do the bitwise OR. Not all that complicated. I'll just say OR is similar. All right. How about bitwise addition? This is the real deal here. Bitwise addition. This is similar, although this time you are going to have to worry about carries. So as an example, if I had something like 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, and let's say I want to add those. I'm going to assume that the number of digits is equal in the two numbers I'm adding. And if they're not equal, you can just insert extra zeros on the left end. So we'll assume we have the same number of digits when we're adding them. All right. Let's just see, can we do this one by hand? You add vertically, moving right to left. So 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, and I carry a 1. Here I have 1, 0, 0. That gives me a 1, and then 0 plus 1 here is a 1. So that should be the answer if I do it by hand. Basically, what you see here is if there was a stacked input like that, this becomes a 1, right? Just like you saw right here. I have a digit 0 stacked on a 1. That becomes a 1. I will say parenthetically, if there was no carry. Right? If I had a carry going into this position, then that would change things a bit. But if there was no carry, then it would turn out like that. The way you want to think of this is, as you go from digit to digit, we need to keep track of if there was a carry or not, because that changes the answer. Depending on if there has been a carry from a previous digit, it's going to change the answer. So we need to keep track of if there was a carry or not. All right, and the way that we can make this work is by having two states where our previous machines had only one state, and they are going to represent if there was a carry or not. So I will say I'm going to have, say, a no carry state. Remember when I used to give names to the states? Remember those days? There's like a no carry state and a carry state. And my starting state will, as usual, we have to move to the right to the end, which is going to be kind of a pain here because the tape begins with stacked inputs. So you have to do something like this. If it's a 0, 0, you move past it. If it's a 0, 1, we have actually 4 different alternatives here. It could be a 1, 0. It could be a 1, 1. All right. Anyway, eventually we will get to a blank. We back up by one position, and then we're ready to begin. My first arrow then, it should either go into here or here, depending on the rightmost digit. When we get there, should we be considering was there a carry from before, or should we start off with no carry? What do you say? Start with no carry. Yeah, every kid knows that, right? No kid ever asked, hey teacher, should I be carrying on the first digit? No, you should not, kid. So when we begin, you begin in the no carry state, all right? This is a B, L, right? I eventually went all the way, you overshoot the end and then you back up by one position. We are in a no carry state. All right, and I think I need a little more room here. We got 5 minutes to do this. I think we can handle it. We just have to think about, if I'm in the no carry, for example, in the no carry, if we see 0 stacked with 0, we make it a 0, right? Because you would actually add the 2 digits, 0 plus 0 becomes a 0, and then move to the left, and should we have a carry after that or not? Not, because I added 0 plus 0, I got 0. That does not require any carry. We make it 0 and no carry, right? And so that would correspond to a looped edge like this, 0, 0, 0, L. That L because in the next step we need to go back. We need to continue on to the next digit, which is to the left. All right? So if you see 0, 0 in the no carry state, you mark a 0 and move back left. And I'm just going to try and do little reasonings like this every time. What if it's a 0, 1? What should the answer be? And then does it require a carry? What do you say? What should the answer be then? Yeah? A 1 with no carry. Yeah, so here, if I see 0, 1, I make it a 1. And still no carry. That's why it's on this loop back to the no carry state. All right? Similar for 1 over 0, right? 1, 0, make it a 1, move left. The only time you might get a carry is if you're in the no carry state and you see a 1, 1, right? Then you have to go down this way. What should I write as the answer in that digit? A 0, yeah. If you see a 1 plus a 1, you write a 0 there and then you carry. So this becomes a 0 and a L. All right? And then I have to think about, in the carry state, what happens for various inputs. For instance, in the carry state, if we see, I'll start with 0 over 0 again. What should the answer be there? If we have an old carry and the digits I see are 0 and 0, then the answer should be 1. And we should not carry into the next digit. So you make it 1 and then no carry. So this is an arrow going back here, 0, 0, 1, L. Oops, like that. Back to the no carry. I think actually in all other cases, we need to continue to carry. These would be loops. For instance, 0, 1. Think about if you see 0 and 1 and you have a carry, then what should the answer be? It should be 0 with another carry. And so that's why this is looping back to the carry state, and I write a 0 here. Same for 1, 0. And what about 1, 1? If it was 1, 1 and you also had a carry, I should mark a 1 in that position and also carry. So that's like that. This is basically it. Almost. We got 1 more minute. We can handle that. What else do we need here? You should think about what happens at the end, right? At the end, you arrive at a blank. Now, if you're in the no carry and you get to a blank, you should just stop and be done with it. If you were carrying, though, when you got to the very end, you have to add an extra digit at the end if you carried all the way to the end. So from the carry state, if I see blank, I write a 1 and then stop. From the no carry state, when you see a blank, you can just stop and you don't have to do anything because it'll just stop with no arrow. There you go. This is bitwise adding on a Turing machine. Pretty cute. I want to try subtracting next time. It's similar.